This is Lab 2 Charge Tape Revisited. So our purpose of this lab is to observe the interactions of line charges using the interactions of two pieces of charged tape. We're going to further investigate Lab 1 results by using a more sophisticated model for calculating the electric force and charge on charged tape. So we're going to use line charge instead of point charge this time. Our preview are listed here, so we have the magnitude of the charged tape is this, which is roughly 2.5 times greater than that of the point charge from Lab 1, which was this number right here. And we found that the magnitude of gravitational and electrical force is this right here. So our introduction, our fundamental principles are similar to the first lab. We have Newton's second law and gravitational force. Force equals mass times acceleration, with acceleration being 9.8 meters per second squared, which is the acceleration due to gravity. And then Coulomb's law is the force between 2 point charges. So we have Coulomb's constant times the 2 point charges over the magnitude of the distance between the two charges squared. It also tells us that opposite charges attract and like charges repel. There is also the electric field of a point charge, which is Coulomb's constant times 1 of the charges over the distance between the 2 points, magnitude squared. And then the electric force of a point charge takes the E field and multiplies it by our observation location's charge. Alright, and then the other fundamental principles are the superposition principle. It just tells us that we can take the forces or E fields, whatever we want to take for each little charge or point, and then add them together, and that will give us the net, whatever we're looking at. And then polarization is the slight separation of positive and negative charges in an atom or material. And then the electric field of a line charge, we're going to use the superposition principle, and basically we're going to chop up each of the tapes and look at the total E force that it contributes on each little point, and then add those up for the top tape, and then get the full net E force on it. And that we'll discuss that further in the code. So the procedure is the same as Lab 1. Our system is tape B, surrounding is tape A, and everything else. We charge the tape, we observe the interactions, and we use code to get the force and charge. We assume that each tape has the same net charge evenly distributed across the piece of tape. We are treating each tape like it's a line charge instead of a point charge, and air resistance is still negligible. Our observations were that the tape repel, which show they're like charges, and they're both positively charged, as they both were attracted to the negatively charged pen. Again, observations are the same as Lab 1. These are our initial conditions listed here, length, width, mass, and distance between the tape. These are also some of our calculations we got from the code. So we have the magnitude of electrical force, gravitational force, and the charge on the tape, which this one was used for, we do trial and error, and then magnitude of the electrical force was the sum of the forces on the top tape, which we did in the code here. So again, we found that the magnitude of the charge of one piece of tape was this number right here, which is greater than the one from Lab 1. And we found that by using trial and error to find Q until electric force and gravitational force were even. As I go through this code, my code is in the comments if you guys want to follow along with that. It is available. To start, I had Lab 1 charge, and I just kind of multiplied it until the forces equaled each other. Because we know they have to equal each other because they need to cancel each other out, because the net force at tape B, which is this red line right here, is going to be 0. So this yellow line is the gravitational force, and this top line is the electrical force. These little ones are the E fields from all these point charges right here. So we have the initial conditions written out here. Then we made our function from Lab 0 for the E field, which we use this equation right here. And then this shows us how we sectioned out our top tape and bottom tape. So I chose the number of slices that were needed on the tapes, because whenever I chose 50, it was a good enough estimate where choosing more like 100 or something, it didn't change the charge enough to really make a difference. And then this is making the line a charge. Like, so it takes the total mass and the total charge, and it divides it by the number of sections we created in the tape, and we'll use that later in here. So this is just the scalar values of the arrows that I use. I just did trial and error. And then these 4 loops are what creates the net electric field at the top, and then also the net electric force. So basically this first one calculates the E field at the locations, and we use our little function that we created earlier. And then this line here, the electric force, we took the charge that we're looking at and multiplied it by the E field, which again is from this equation right here. And then at the end, we have the electric force and the gravitational force, and then I added the magnitude of the charge so that I could keep track of what Q was. So the potential errors in this lab are the charge may not have been equally distributed, some of the charge may have been lost due to mishandling or inaccurate measurings of anything like that. So what if you had modeled each of your tapes as a single point charge, like in the previous lab? Compare the two. So the charge modeled as a line is, again, this many coulombs, which is, again, roughly 2.5 times greater than the charge from the first lab, which is about this right here, and so where the tapes were modeled like a point charge, like I just said. So those are the two, and then why do they differ? They differ because the point charge takes all of the charge along a distance and squeezes it together to one point. The line charge lets you lets the charge be evenly distributed, which is going to be a lot closer to the real value, because in reality, the tape would not just have one point on it have all of the charge. It would more likely be maybe not evenly distributed, but distributed somehow across the tape. Yeah, and it's more likely closer to the real value because, again, like we're using the superposition principle, so we can sum all of the charges along the line. While it's not going to be exact, it's going to be a much better value because it's closer to real life. Thank you.